going to talk about infinities. Okay, so infinities. There's a notion in mathematics called a one-to-one correspondence. And so that is like if we're looking at the members of this class, right? There are 7 of you here. You could have a correspondence between you and some other object of some other set of 7 objects, right? Or you could have a one-to-one correspondence. You could say, you know, one is Flo, 2 is Alana, right? Down to 7 is Sarah, right? You could have this a one-to-one correspondence, like you know, each element in the first set corresponds only to one and only one element in the second set. And if that happens, then we consider the 2 sets to have the same size, right? So if if there exists a one-to-one correspondence between 2 sets, A and B, we say that the number of elements in A equals the number of elements in B. Okay, like this is read the cardinality of A equals the cardinality of B. Okay, so for example, if we're looking at the natural numbers, right, the natural numbers 1, 2, 3, 4, 5, blah blah blah, and we're looking at the integers. Right? We're looking at the integers. Well, actually, you know, the integers have the same cardinality as the natural numbers, right? You can say, well, oops, 0, 1, negative 1, 2, negative 2, 3, negative 3, etc., etc. Right? And you could make a one-to-one correspondence between these guys. And so the infinity of, you know, the number of elements here is infinite, and the number of elements is here infinite, and we consider these things to be the same, same infinity. Okay. What about Q? What about the rational numbers? Do you think you can make a one-to-one correspondence between the rational numbers and the and these guys? What about Q? It actually turns out that it's possible. It actually turns out that the cardinality of Q is the same thing as the cardinality of Z, the same thing as the cardinality of N. And all these things are denoted, I forget how to write it, something like this. There's some Hebrew letter called Aleph, and we put a 0 under it, so it's called Aleph not. Aleph not. And that's considered to be the first infinity, right? Aleph 0, the first infinity. Okay, it turns out that all these things have the same cardinality. One way you can start to see that happens is that you could say, well, if I'm looking at the rational numbers between 0 and 1, so consider the rational numbers in 0, 1, in the interval 0, 1. You can actually make that into a list. You say, well, I'm going to have 0, I have 1, then I have a half, I have 2 halves. I'm being redundant, but well, maybe let's not be redundant. Okay, let's skip. Okay, I've got 1 half, I've got 1/3, 2/3, right? I've got 1/4. I'm going to skip 2/4 because I have it already. 3/4, right? I've got 1/5, blah blah blah. And you see that I can make a list, right? And every rational number between 0 and 1 is going to be on this list, right? If you choose a rational number between 0 and 1, I'm guaranteed I'm going to hit it eventually, right? I'm going to hit it only one time. And so basically any set that you can put in a list like this has the same cardinality. And these things are called countably infinite sets. Countably infinite. So it turns out that Q is actually pretty sparse. It's actually pretty sparse. in the following sense. So this is just for fun again. How much material do you need to cover up? Suppose this thing is 1 meter long. Okay. I say, how much material do you need to cover all the rational numbers between 0 and 1? The answer is as little as you desire. Okay, as little as you desire. Why? Because suppose I take a centimeter. Okay, I take a centimeter of material, and I use half of it to cover 0. I use a half of what's remaining to cover 1. I use to cover 1. I use a half of what's remaining to cover 1/2, etc., etc. I keep on going like this, and you see that I've covered every, for every rational number, there's some point where I will cover it, right? And I cover it with with some thickness, right? Right, 1/2 to the n, where n is the position on the list, right? So I can cover every rational number with as little material as I desire. With as little material as I desire. That should be sort of strange. Like all the rational numbers in here can be covered with this much material. In fact, smaller than that, right? You take as tiny amount of material as you start off with, and you can cover the rational numbers with that, as long as it's some positive number, right? So, in other words, if I chose a number between 0 and 1 at random, what's my chance of getting a rational number? What's my chance of getting a rational number? Is it large? Is my chance of getting a rational number large? No, not at all, right? It's almost 0. It is 0, right? The chance of getting a rational number, if I throw a some sort of dart at the numbers here, the chance of me landing exactly on a rational number is the chance of me hitting this much material, hitting this much material in all of this, right? In other words, the irrational numbers actually make up the majority, the vast majority of the numbers. Okay. This should give you a hint as the answer to the next question. What about the real numbers? Do you think that we can make a 1-to-1 correspondence between these guys and these guys? Right? At this point, you think no, right? Absolutely not, because you're thinking, well, if we could, that would mean that we could cover the real numbers also with that little amount of material, but that's impossible. This actually has some length here, right? So at least you don't believe it for that reason, right? You say, well, it's not possible, and so the cardinality of the real numbers is actually a bigger infinity. It's infinite also, but it actually turns out to be a bigger infinity than these guys. It's usually called C, or sometimes it's called aleph 1 for the next next infinity. C for the continuum. Right, it's a continuous thing, and you have this continuum of that's another kind of infinity. Okay. There actually is something called this famous question called the continuum hypothesis. And I believe it's still unsolved, although I'm not sure. Unsolved question, is there any infinity that lies between this infinity and that infinity? Is there some infinity between them? Right. Okay, and it turns out, so what we're seeing here is that this infinity is actually bigger than that infinity. So you've got this other infinity. Okay. So let me show you one more thing, and then we'll get back to the movie. So there's a famous argument. Famous argument showing that the real numbers cannot be countable, and that there's no way to put these guys in a list. Okay, so that this infinity is definitely not the same thing as that infinity. Okay, and this is called Cantor's diagonal argument. It basically goes like this. You say, consider all numbers between 0 and 1. All numbers in the interval 0, 1. Okay. And let's use binary notation for them. Suppose we use binary notation rather than decimal notation. It doesn't really matter. We could use decimal notation, but all these guys are going to be expressed as like sequences of zeros and ones. Right? This is some number between 0 and 1. Every number between 0 and 1 you can express in some infinite binary sequence. Right? Okay. So So here it goes. You say, well, suppose there is a list of these numbers. Right? In other words, that this set is countable. Suppose that it's countable. Okay. And suppose, let's say that, here it is. Here's the first number on the list, here's the second number, here's the third, fourth. Okay, suppose there's a list, A sub n, and somebody says, you told me that the real numbers are not countable, but here they are. I've made a list of the real numbers. Okay, I've made a list, and this list hits every single number between 0 and 1. Okay. So what you do to such a person is you'd say, okay, let's look at the binary representations of those guys. And again, it doesn't have to be binary, but it would be convenient to do that. Okay. Suppose you have some binary representation of A1. It's going to be like x1. How should I do this? It's going to be x11, x12, x13, x14, x15, blah, blah, blah. This one's going to be point x21, x22, x23, x24, x25, blah, blah, blah. Point x31, x32, x33, etc., etc. Okay, so each of these things is 0 or is some number, 0 or 1. Okay, so this is you take the binary representations. Each of these guys is, and here it is. This is something like 1, 0, 1, 1, 1, 1, whatever. So you say, okay, give me your list, and I'm going to write down all the numbers. Okay, I'm going to put all the numbers down. You said that this has all the numbers between 0 and 1. Okay, and what you do is you do the following: you make a number by taking these guys down the diagonal. You make a number by going down the diagonal. And you create a new number. Okay. That number is x11, x22, x33, blah, 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 blah. Okay. And then you toggle every entry. If this was a 0, you turn it into a 1. Okay. So let x twiddle be 0 if x is 1, and 1 if x is 0. Okay. Right. So then you say, well, consider this number. Right? This number, which is basically 1 minus the previous number. Okay. Okay. You say, okay, is this number on your list? Is this number on your list? And the answer is no. Why not? Why not? Well, is it equal to the first number? No, because its first entry is different from that guy's first entry. Is it equal to the second number? No. Its second entry differs from the second number's second entry. Right? Is it the third number? No. Its third entry, its third place in the third digit, it differs from the third number's third digit, and so on and so forth. Right? So the number you create here is not on the list. right? It differs from all the numbers. And you say, well, you told me that this list had all the numbers. If this list had all the numbers, why isn't this on it, right? So that no matter what list is given to you, there's always a number. You can always create a number that's not on that list. Okay, so there's no list that's complete, right? So you end up with a contradiction. The list, the complete list, didn't include, doesn't have this number. And so you get a contradiction. You get a contradiction, and that shows you that there couldn't that the real numbers could not have been counted. The real numbers are not a countable infinity. There's something called an uncountable infinity. Okay, well that was just for fun.